So, now let us take some examples on the phenomenon associated with surface tension. We will use how to use the effect of surface tension to explain these situations. So, example 1. So, here we have n identical drops of liquids of radius small r. So, this is n drops, and when I mix it, it becomes a big drop. So, find the energy liberated, find the heat produced in such mixing process. So, first of all, let us see that what is the radius r dash which will be formed by adding all the liquids here. So, let the radius of the big drop formed by n droplets be r dash. So, the volume of this, since mass is conserved, so rho into 4 by 3 pi r dash cube is rho into n times 4 by 3 pi r cube. So, rho and 4 by 3 pi cancels. So, r dash is equal to r times cube root of n. So, we got r dash. So, now you see, so what happens, the surface area is decreased. So, the decrease in surface area, means the decrease in surface energy. So, what amount of energy appears is this? So, initial surface energy is equal to final surface energy plus delta Q. So, initial surface energy, you see this is not surface energy, free surface energy, let us write it free surface energy. So, initial free surface energy is equal to final free surface energy plus delta Q, and this is S into n times 4 pi r square. This is S into only 4 pi r dash whole square plus delta Q. So, you see here S into n into 4 pi r square is equal to S into 4 pi, this r dash means r square, then n to the power 2 by 3 plus delta Q. So, we have delta Q equal to, we will subtract this. So, we will have 4 pi s common, here we have nr square, we can take r square also common. So, only n will be there, only n minus this 4 pi r square common, n to the power 2 by 3. So, this is the energy liberated when n drops combine to form a mega drop. Now, we have two soap bubbles of different radii who adhere, means just they are touching each other. So, we have two soap bubbles, just imagine this is one big bubble and we have another big bubble, and they are allowed to just touch, they are not allowed to communicate the air trapped inside it. So, we have air here, So, this is R1, smaller one, and R2 bigger one. So, two soap bubbles, these are bubbles of radii R1 and R2 adhere to each other. adhere to each other. The gas inside them is not communicating. That means the gas is trapped inside it. Find the radius of curvature of the sandwiched surface. Also find the angle between the surfaces near the contact. So now you see here another diagram I am doing. This is our bigger one, R2, and you can see this inner one, this is R1 and this is R2. This is the modified surface, suppose I say. So you see here, or let it be something, it is like this, suppose like this. So we have to find its radius of curvature. So we have 2 points, suppose I say it is point 1 and point 2. So this surface separates the content of 1 and 2. So let us first find P1. Now from this bubble, this is a bubble with air inside this and outside. The pressure inside P naught, inside the bubble 1 is P1 equal to P1 P naught plus 4s by R1, and also P2 is equal to P naught plus 4s by R2. Now this is smaller, so P1 is thus P1 is larger than P2. That means the concave side is here. Thus the concave side of the sandwiched surface is along R1, is in that circle. Now what is the radius of curvature? So again applying excess pressure formula over this, we have P1 minus P2 as 4s by R. Why 4s? Because this is a drop, this is a bubble which has 2 surfaces. So we have thus P1 P naught plus 4s by R1, P2 that is P naught minus 4s by R2, that is equal to 4s by R. So P naught cancels. So 1 by R is equal to 1 by R1 minus 1 by R2. So now let us see the angle between the 2 drops. So you see here, this is the big drop bubble, and we have to coalesce this. So in order to draw, you see here what we do. So here is the tangential force, and here we have one more tangential force, and suppose these are the force triangles. So here you see it is somewhat, suppose I draw like this. This is the liquid drop bubble, and you can see the interface here. Now how to draw this? You see here, you just imagine here that there are 2 surfaces, and you see since air is inside it here. So suppose I just imagine on this curved surface a small length, then here you will have 2s, the surface, two surfaces is there. If there is only one, then s into dl, so 2s dl, here 2s dl, and again here 2s dl. So these are equal forces, so they must be equal, and so they must be inclined at 120 degree. So here also you can see the forces will be like this, equal forces. So at these two junctions, the angle between the two surfaces is going to be 120, 120, between these two 120, and again in between these two also 120. So thus the angle between the two surfaces, that is at the interface here, is 120, 120, 120. This is how the tangents will be, and the shape of the two adhering drops, bubbles will be. Let us take another example where we have two liquid drops. So two liquid bubbles. Suppose this is liquid bubble, and so this is of radius r1, and another one of radius r2 is there, and I want to know how much radius of the new bubble will be formed. So two soap bubbles of radii r1 and r2 coalesce to form a big bubble. Now let us find the radius of the new bubble. So here we should keep in mind that whatever the gas is here, whatever the gas is, that the total gas present, the M1 mass, M2 mass must be the same. So suppose here the pressure is P1, so applying ideal gas law. So here pressure is P1, 4 by 3 pi R1 cube is equal to N1 RT. And so here you see we got N1 as P1, let it be simply V1, only V1 is the volume, suppose I say P1 V1 by RT. And so N2 will be also P2 V2 by RT. Now what we can equate it here, the total number of moles is the N, here N is the number of moles, that is equal to N. So what is N1? So N1 is P1 V1 by RT plus P2 V2 by RT, that is equal to P new volume V by RT. So we have R, T, we have cancelled. So we have P1 V1. Now what is P1? P1 is the pressure inside it. This is P0 plus 4S by R1 into 4 by 3 pi R1 cube plus P2 V2. P2 is P0 plus 4S by R2 into 4 by 3 pi R2 cube is equal to pressure. Here pressure is P0 plus 4S by R by 4 by 3 pi R cube. So you see 4 by 3 cancels out. So we have P0 plus 4S by R1 times R1 cube plus P0 plus 4S by R2 times R2 cube is equal to P0 plus 4S by R by R cube. So from this equation, this is a cubic equation, the expression of R can be determined. So it's not cubic, some power is there. So the expression of R can be determined from this expression. So now let us consider a drop of thickness T, and this drop is allowed to fall freely. A water drop is allowed to fall freely. Fall freely. It falls with a constant terminal velocity. Terminal velocity. Find the difference of the radius of curvature of the lowest or lower part to the upper part. The distance between thickness of the drop at its center is t. So now let us calculate the radius of curvature at this point and this point. So number one point is that suppose if a drop is allowed to fall freely, if a drop is allowed to fall freely, then 1, 2, then the pressure at 1 and 2 is same. There is no H rho G between these two. The difference of pressure with height between 1 and 2 will not be there, because everything is in a state of free fall. There is no pressure variation along this 1 and 2. Same, and the shape is spherical. The shape is spherical. So it is under free fall. Now when it is under free fall and due to viscous drag of air, it comes with a terminal velocity, then the pressure at 1 and 2 is different because of variation of pressure with gravity. So they will feel the effect of gravity, and so there is a pressure variation with gravity, and so P1 and P2 will be different, and so the shape will not be spherical but somewhat distorted sphere. So we have to calculate that if it is falling down with a terminal velocities, then what is the difference of the radius of curvature and these 2 points. Let us do now. So now let us take a point 1 and 2. It has a radius of curvature here R1 and here R2. So this is a drop. So this is a liquid drop. Now applying excess pressure formula for upper surface. So this side, concave side, has one P1. P1 is more than the atmospheric pressure P0 by, this is drop 2s by R1. So this is equation number 1. Again applying excess pressure formula for the lower surface. So P2 minus P0 is equal to 2s by R2. This is 2. So from 1 and 2. So if I subtract here, you see this. One more thing, this is P1 minus P2. P2 is more than, so let us from 1 and 2 I subtract P2 with P1, then I will get 2s by R2 minus 2s by R1. Now P2 will be equal to P1 plus h rho g, where h or t rho g. So this height is, this thickness is t. So, we have T rho G is equal to 2S by R1 minus R2 by R1 R2, implies delta R, that is R1 minus R2, is T rho G R1 R2 by 2S. Now, you see here this R1 is nearly equal to R2 is equal to T by 2. So, we have R1 R2. So, I will write T square. So, it becomes T cube rho G by, this is 2. So, 2 into 2 4 into 2 8S. So, this is the difference of the radius of curvature of the lower part and the upper part. Now, let us take a fifth example where we will be using Bernoulli's theorem. We have a jet of water falling like this. Here the diameter is d1 is equal to 2 mm, and after falling certain height h, the diameter d2 becomes 1 mm. That is, it becomes d2 is equal to eta times d1. So, now you see this liquid jet is coming out and falling, and we have to find the discharge. What is the discharge of liquid through this? So, now you see here the area is here something. So, the discharge Q is equal to rho times the velocity here. So, discharge is area into V, that is pi d square by 4 into V1, that is eta times pi d square by 4 into V2, number 1. Next point, we can use continuity equation also, that is the same discharge. So, this equation is also the continuity, and I have to write V1 V2 in terms of discharge. Now, we have to take and apply Bernoulli's theorem at 2 points on the streamline 1 and 2. So, applying Bernoulli's theorem on the streamline at 1 and 2. So, you see I am assuming a streamline here inside this, and so this point is 2 inside and this is point 1 inside. So, the pressure energy is P1 plus rho V1 square by 2 plus rho G Z1 is equal to P2 plus rho V2 square by 2 plus rho G Z2. So, if I assume this as to be the datum, that means this potential energy is going to be 0, gravitational. Now, P1, so let me be P1. So, what is pressure here and what is the pressure P2 here? So, now here you see this I can approximate as a cylindrical surface. So, inside the cylindrical surface, you can see this is the cylindrical surface. The pressure is more than outside. So, P2 will be more than the outside P naught by how much amount? By this is equal to P naught plus S by R, radius. Why you can see? You can see this is a cylindrical surface. So, excess pressure formula for cylindrical surface is P is equal to S by 1 by R1 plus 1 by R2, S into 1 by R plus 1 by infinity. This is infinity 0. In terms of D, I can write R is equal to D by 2, 2S by D, where D is the diameter at that point. So, from this I can say P1 is equal to 2S by D and P2 is equal to, this is P1 and P2, P1 and P2, that is 2s by d by eta. So, this is eta times the initial d. So, thus we will put these values, that is the excess pressure, sorry, this is excess pressure. So, P1 is equal to P naught plus 2s by d and P2 is equal to P naught plus 2s eta by d. So, we have to substitute this value here. So, now substituting these values in P1, we have P naught plus 2s by d. This is the pressure P1. From this discharge, this we will put this discharge equation, that discharge is the area, that is pi d square by 4 into V1. So, we will have rho by 2 as V1 square by 2, that is rho by 2 V1 square, that is pi square d to the power 4 by 16 plus this is rho GH is equal to P naught plus this one 2s eta by d plus potential energy 0 and kinetic energy rho by 2 pi square by 16. Here one more thing, q, here V is q by pi d square. So, here it is actually wrong. Let it be rho V square by 2 only. So, let here be rho V square V1 and here it be rho V2 square by 2. So, now we have this equation. So, now we know the discharge equation, that we can put it here. Let us simplify it first. So, P naught cancels. So, we have here 2s by d 1 minus eta plus rho GH is equal to rho V2 square minus V1 square. So, that is V2 square minus V1 square becomes 2 by rho 2s by d 1 minus eta plus rho GH. This is equation number 1. Now, I know V2 and V1 here. So, I can calculate discharge. I will put the expression of discharge is equal to area pi d square by 4 into V1. Discharge is equal to pi d square eta square by 4 V2. So, in place of V1 and V2, I will put Q, and so we will get the value of discharge from this equation. So, here Bernoulli's equation along with the pressure that has to be calculated by surface tension. Now, if this is in millimeters, then only surface tension forces can dominate. If it is in meters, then that surface tension forces will be so small that I can neglect this effect. But since they are small, so I have to take this into account.